Recent analyses of surface samples gathered from the far side of the Moon have brought to light a game-changing reality about the chemical boundaries of the universe. Samples brought back to Earth by China's Chang'e 6 spacecraft were examined, and according to analyses published in January 2026, single-walled carbon nanotubes, which have never before been seen in nature, were found in the lunar soil. This discovery is vital because we believed we could only produce this material in laboratory environments under very specific conditions. However, this finding proves that this substance may have existed on the Moon for billions of years. Carbon nanotubes are cylindrical structures formed by carbon atoms arranged in hexagonal lattices. They are thousands of times thinner than a human hair, yet 100 times stronger than the toughest known steel and 85% lighter. Thanks to their perfect atomic alignment, these materials are considered both superconductors and one of the strongest substances in the world. Producing these structures on Earth is an extremely challenging process. Scientists require laboratory temperatures exceeding 1,000 degrees, vacuum chambers, and control mechanisms with millimetric precision. Controlling the atomic alignment of single-walled nanotubes specifically is seen as one of the greatest challenges of modern technology. Unlike multi-walled structures, single-walled nanotubes are like atomic superhighways that contain no structural flaws and conduct electricity and heat perfectly. The reason such a difficult-to-produce material is so valuable lies in the unlimited technological possibilities it offers. Because they are so hard to manufacture, carbon nanotubes are regarded as the holy grail of technology. Today, we use this material to revolutionize long-life batteries, medical technologies that target cancer cells with pinpoint accuracy, and computer chips. In the future, we know they will make everything from aircraft fuselages to futuristic armor much lighter and more durable. So, how did the Moon achieve this without the environments we build in our labs? The answer is hidden in the turbulent past of the Moon's far side. This region is exposed to much more frequent and violent meteor bombardment compared to the near side. The instantaneous, massive energy generated by micrometeorite impacts, combined with iron minerals in the soil, transforms the surface into a kind of natural nano-factory. Within this chaos, carbon atoms might be using iron as a guide to form these massive tube structures. Radiation from solar winds further reinforces this process. This discovery proves that the Moon is not just a dead piece of rock, but a massive natural laboratory where extreme chemical processes take place. The data brought by Chang'e 6 could radically change in situ resource utilization strategies for future space missions. Considering the massive cost of transporting materials from Earth to the Moon, these naturally occurring carbon nanotubes on the lunar surface could be the fundamental building blocks for constructing future moon bases and producing radiation shields. What is truly exciting for the scientific world is understanding how these perfect structures, which are difficult to produce even in a laboratory environment, synthesized themselves in the harsh nature of the Moon. These natural nano-factories on the far side of the Moon show that matter can transform into its most perfect forms even under the universe's harshest conditions. We are no longer just looking at the Moon. By deciphering this atomic engineering hidden in its multi-billion-year geological history, we are redefining the physical limits of our deep space exploration.